Live. I think we're live. It's red in the corner. Let's give everything a refresh, see if it pops up. It has popped up. So let's get that open. Lovely. So yeah, I'm going to be walking through. This is the IYGB, the past papers for A-level maths. These are generally like the kind of harder ones. This is paper B. So I'm going to do the full walkthrough. I have another lesson at 7, so hopefully I'll get it done in time. Like I say, if you've got any questions at all, just give me a shout. And I will answer them in the chat if I can get everything to be working correctly. I will just keep double checking. It says I'm live now. Yes, lovely. Everything looks to be good. Everything's working correctly. So let's get going. So question 1, we want to write the following surd expressions as simple as possible. So that means the lowest number inside the surd, basically. The 6 and the 24, we need to reduce them if we can. What we're looking for is square factors of each number. 6 has factors of 2 and 3. Neither of those are square, so we can just leave the 6 alone. The 24, we can rewrite as 24 is the same as 4 times 6. So we can square root both sides. That square root on the right-hand side, we can separate out into root 4 and root 6. And the root 4 we can evaluate to give us just 2. So we've got 2 root 6 for the root 24. So this ends up being 2 root 6 plus root 6, which is the same as 3 lots of root 6. Lovely jubbly. For part B, it'll probably end in a similar sort of thing. But to start with, we'll do FOIL. So the 2 times the 4 will give us an 8. 2 times negative root 12 is 2 root 12, and again negative. 3 root 4, well, root 3 and 4 will give us 4 root 3. Both positive, so both positive at the end. And then we've got root 3 and root 12. So that's going to be root 36, which is just 6. We had 1 negative, so we have a negative as well. The next bit then is just to look at this. 3 is a prime number, so that surd cannot be simplified at all. 12, you can see, has a factor of 3. So it's going to follow a very similar path here. And actually, you can see it's going to be just kind of double the one that we've got up there in a weird way. Not quite double, but root 2 as big. So let's look at the... Or more importantly, yeah, we'll do 2 root 12. So that's the same as 2 lots of root 4 times 3. And again, we can separate them out into 2 times by the root 4 times by root 3. And the root 4 we can evaluate to 2. 2 times a 2 gives us a 4. So this whole bit was 4 root 3. This whole bit is 4 root 3. 1 was negative, 1 was positive. So they cancel out with each other. So all we're left with, 8 take away 6, gives us a 2 altogether. So that's question 1, all done. Nothing looks to be too complicated in there, so fingers crossed, no mistakes there. If I have time at the end, like I said, I've got a lesson at 7, so what, an hour and a quarter. If I have time at the end, I will double check. If not, I will kind of post in the comments or something if I made a mistake at the very end. Let's keep going. So what else have we got? Question 2, find the set of values for x that satisfy the following inequality. So you've got to be a little bit careful here when we start times in by numbers, because whenever we times by negative, that's going to flip the sign over. So if you think about x minus 1, if x minus 1 is positive, that tells us that x is bigger than 1. So in that case, nothing's going to change. So basically, we're going to have 2 different ways of thinking about it. One when x is bigger than 1, and one I'll do on the left-hand side when x is smaller than 1. On this case, we know that x minus 1 was negative. So we've multiplied by something that is negative. So we have to flip the direction of the sign. So we're going to have the 4x. We'll have 3 lots of x minus 1 on this side. And like we said, we flip the sign because in this case, this entire bracket was negative. So doing that, instead of it being a greater than sign, it's going to be a less than sign. Let's expand those right-hand sides. We've got 3x and a minus 3. Still the 4x plus 1 on this side. We can subtract 3x on both sides. So 3x is left on 3x is left. A single x is left on the left-hand side. And we'll take away the 1. So we have x is less than minus 4 altogether. By doing that minus 3, take away the 1. If we look on this side, like I say, x minus 1 was positive. So we're multiplying by something that is positive. So we don't need to change the sign at all. So it's going to be a very similar looking thing. In fact, with the expansion is the same. It's just the sign is the other way around. So what we're going to end up seeing is that we've got 4x plus 1 is greater than 3x minus 3. So x is greater than minus 4. That seems to be wrong because we've obviously got to split every single number apart from 4. I will circle back to that one. That looks like there's something gone wrong in that scenario. So we won't worry too much about that one, but I will come back to that in a second. Am I just overcomplicating it? I may well be overcomplicating it a little bit. Yeah, we'll come back to that at the end. I will make a little note on my side here. Question 2. So for this one, question 3, we've got some quadratic function. Show that it's always even whenever we put in a number that is a whole positive number. So doing that, what we can do is factorize this to begin with. So that's a nice simple one to factorize. We'll get 2 brackets where we're going to have n in both. Nice and simple because we're making the n squared. When does that come from? It's just the 2 n's in here. Where does this 2 come from at the end? It's going to be these 2 numbers times together. So it's going to be 2 and a 1. And then you have to add up to make 1. Oh, no, not quite. Not even going to factorize in that sort of way. Do we do something slightly different to show that it's even? Yes, we do. Okay, a bit sneaky. So if this was a minus 1 in the middle, we'd have the 2 in the... No, if this was a minus 2 at the end, you'd have 1 positive, 1 negative, which would give us the positive 1. But because it's not, we're going to have to split it up slightly differently. So instead of it being 2 brackets, what we're going to have is let's just kind of factorize those n parts. So we'll take an n out and an n plus 1, and then still have that plus 2 on the end. What we have here, these are consecutive integers. So we've got one number and the number next to it. One of these is even, without a doubt. 2 is also even. When we add 2 even things together, we end up with an even number. So I think I'd just write that down. I'd say that n plus 1 are consecutive. Consecutive positive integers. We know that because n is a natural number. So positive integers. Therefore, at least 1, well, exactly 1. Therefore, 1 is even. And we know even times odd gives us an even. And if we do even plus that 2 on the end, even plus 2 is always as well an even number. So that should be good enough for the marks. We've followed a nice chain of logic. We've got out to a position that looks quite good. So happy days for me. I think that all looks spot on. I'll go to number 4. We want to solve this equation equal to 0. So we just need to factorize this quadratic. In the exam, you can just whack that in the computer or in your calculator, get the values and then give the solution. Should be fine. Here I will work through it though. So I've got not very nice numbers, like 4 is quite big there. So what we can do is do the 4 times the 25, gives us 100. Factors of 100 that have a difference of 20. Well, what factors could we get? 101, 2 and 50, 3, nope, 4 and 25. We're getting close now. 5 and 20. That's not looking good either. What other numbers could we get? 6, no. 7, no. 8, no either. 10 and 10. 10 and nice and simple in there, 10 and 10. So we can split that 20x into 2 lots of 10. And then from there, we can factorize each one separately, like the first 2 and the last 2. So think about these 2 parts and these 2 parts. The first 2, we can take a factor of 2 and x at the front. And then we'll get a 2x and a 5. And the second one, we can take out a factor of 5 to give us, again, 2x and a 5. So actually here we had 2x plus 5 twice. This is a square quadratic. So f of x is equal to, I've moved up there, 2x plus 5 all squared. So if that equals 0, we know that whole bracket must equal 0. So x is going to be minus 5 on 2. That's for the first part. I will just move this all up a little bit so we've got some more space. For part B, solve when this equation is true. So what we're going to do there is take the kind of final solution that we have, not the very final one, but this 2x plus 5 all squared equal to 0. But now replace the x with a half of x plus 1. So we've got to double this thing. So doubling that, you'd have x plus 2. And then we want to add 5. So x plus 7 altogether. So x plus 7 all squared equals 0. So x should equal to minus 7. We could also probably see this from doing the transformations. Think of what's happened here. This is going to be a stretch of 2 horizontally. So that double that to 5. Have I done it the wrong way round? No, that looks all fine to me. Yeah, everything looks fine there. We could obviously just double check when we plug all the numbers in there, but that looks good to me, and we will then move on. So x is minus 7 for the answer. Doubting myself now. Yeah, so we're going to have the half would have shrunk it down. So this is like the wrong way round in it. So it stretches it by 2, makes that minus 5, and shifts it to the left by 1. That should actually be minus 6. So let's change that around again. So yeah, this is a transformation, an enlargement by a scale factor of a half. Scale factor of 2, 1 over a half. And then it's going to be a shift to the left by 1. So thinking about that way round, we have the minus 5 on 2, transformed into minus 5, it transformed into minus 6. Again, going to double check that one at the end. It's either going to be minus 6 or minus 7. I must have made some little mistake about the expanding there, but hopefully that's not too bad. We'll keep going on number 5. We have some cubic, where we don't know A, we don't know B over here. The graph meets the x-axis at 5, 0. When the equation of C is divided by x minus 1, the remainder is 24. So what that tells us is that when we do the function with 1 subbed in there, it should give us minus 24. So these two parts together are going to give us simultaneous equations. We can think for the 5, we also get the f of 5 is equal to 0. So let's actually just plug those two numbers in, the 1 and the 5, and set them equal to the minus 24 and the 0, and see exactly what's going on. So plugging in the 1 is nice and straightforward. You just add up all the coefficients. So we should get that 6 plus a minus 6 plus b is equal to minus 24. So we can cancel those 6's off. We get that a plus b is negative 24. And when we plug in the 5, it's not going to be as simple. 5 cubed is 125 times by 6 is going to be a very big number. So 5 cubed times 6, 750. Plus we'll have x squared, lots of a. X squared is 25 and times by a. Take away 5 times 6 is 30, and then plus b should equal to 0. Again, we can cancel some of these numbers off. 750 take away 30 is 720, plus still the 25a plus a b is equal to 0. So now we've got these two equations. Again, they exist simultaneously. So we can go through and just try and eliminate one of the variables. We have 25a here and single a there, so not good to work with. But the b's are both just single b's. So if we do a subtraction, let's take this equation here and subtract this one from it. So the 720 is still going to stay there. 25a take a is going to be 24 lots of a. B take b is 0. And 0 take away 24 is going to be 24. So all together then, we now just rearrange this equation for a. 24a is going to be equal to whatever 24 takes 720 is. Gives us minus 696. And now we just need to divide that number by 24 to get the value of a. So divide now by 24 gives us negative 29. We can then go and take this value for a, have a look back at our nice simple equation. A and b together, added up, give us minus 24. So we need to do something, add something to this to get to minus 24. We have to add 5. So that tells us that b is equal to 5. And that hopefully should be all spot on for that one at the top. Let us just shrink this up a little bit, give me some more space to work with. And let's see what's going on now. So I'm going to fully factorize it. So firstly, let's actually write down what we have as just like one full equation. So 6x cubed. A was negative 29. So we've got that many x squareds. We've got the negative 6x and then plus a 5. We want to factorise this. So one way we can think about it is first of all looking at this point. We know it meets at 5, 0. So one of the roots of the graph is going to be 5. So that tells us that one of the brackets is x minus 5. And when we look at the other parts then, there are 2 brackets there, but we can think of them as a single quadratic bracket and try and fill that in and then factorise that quadratic. Because it may well be that these 2, like where we would have 2 of them, they might be complex roots instead, which we don't deal with in single maths. In further maths we'll deal with that, but not in just the single set maths. So how do we actually work out these numbers? Well, let's think about the highest power of x here, the cube. Where does that come from? It's coming from this x and however many x squareds we have here. So we need to do 1x times by something to give us 6x cubed. So it has to be 6x squared. And exactly the same logic happens with our constants. These numbers, this minus 5 and whatever we're missing over here, must be equal to 5. So this number at the end must be a negative 1. And then we need to try and figure out exactly how we're going to get the middle one. When we do that, this x squared, we've got minus 29 of them. Where do they come from in our kind of expansion down here? It's going to come from this x squared here in the constant, or this x and how many x's we have in here. So currently we have minus 5 and 6, which gives us minus 30. I need to have minus 29, so I need to add one more. I've got 1x there, so I need to have just another x to make sure that these times together to give me 1x squared. So this is the quadratic factor that we have here. We can then just go and double check whether we can factorise this bracket again. So I will just have a look at the discriminant, which is going to be b squared. B in this case is 1. So 1 take away 4 times a of 6 times c of minus 1. So that's going to change that to a positive and a 1. And we can see this is going to be positive. So it does have 2 linear factors that we can make from it. So we don't actually need that to actually calculate the answer. That's just making sure that we're not wasting time trying to factorise something that we're unable to factorise. So now then, let's try and split this up. We could probably be a little bit smart from it. Imagine this was a 1 and this was a 6. You would just look for the factors of 6, so 2 and 3, and they would have to be different from the negative and add up to make positive 1. So it'd be like positive 3 and a negative 2. Exactly the same thing happens even though it's a with a big number and like c being small. So we're going to have 2 brackets here. One of them will have 2x, one of them will have 3x. And we need to make sure that we have a positive x squared. So these 2 both have to be the positive parts. And they're both going to have 1s times together to make the 1. And we need to make sure that we get a positive x in the middle. Looking here, this is a negative. So one of these is positive and one is a negative. We're not sure exactly which one yet. But to make the positive 1, we need to make sure that our 3x goes with a positive thing and our 2x goes with a negative thing. So that tells us that we should have a positive here and a negative here. So if we were to expand these brackets, you'd have like the 3x and the 1 to make positive 3x, and the 2x and the minus 1 to make negative 2x. So you end up with 3x minus 2x is a single x up there. So the fully factorised, we still need to bring down that x minus 5. But then these 3 brackets all look pretty good. Part C of this question then is just to sketch it. Show everywhere it crosses the graph and all the axes and stuff. I think for sketching, it's probably easier to just like do that and then fill in the gaps that we have. So firstly, what roots do we actually get from here? We get 5 minus a half and positive a third. So I will just reorder them. Let's bring the 5 to this side so they're in the order, like ascending order. So it's a little bit easier to draw them in. And then where is our y-intercept? It's up here. It's the positive 5 that we have. If we plugged in x as 0, this would be 0, this would be 0, this would be 0. We're left with just a 5 at the end. So that's going to be quite high up. So let's have a look at exactly where the things can go. Draw across there for our 1 axis. We're going to have this number is going to be, negative a half. That's negative a half. This is positive a third. This is positive 5. And we need to make sure that we are between our negatives and positives. So our axis must go somewhere through here. We don't know about the turning point. So all we know is that this point is 5, but we don't know anything about the actual turning point. And they've not asked us for that. They've only asked for when it meets the coordinate axes. So we've ticked all those boxes there. Let's just label our axes X and Y. And label this, do they call it f of X? They just call it Y. So you don't even need to label the graph. That should all be good to rock and roll. Lovely jubbly. Let's have a look at number 6 then. So the gradient function of the curve with this equation, which is y equals 2 lots of x plus a all squared, where a is non-zero, is given by dy dx is 4x plus 10. Determine the value of a. So 2 ways to do it. We can either expand this and differentiate, or we can integrate this and try and figure out what's going on. Let's expand this and differentiate. So if we expand those brackets, what are we going to get? Imagine we don't have the 2 for a second. We'd get an x squared plus a 2 lots of ax plus an a squared. And then the 2 at the front is just going to double all those numbers. So instead of 1x squared, we'll have 2 of them. Instead of 1a squared, we'll have 2 of them. Instead of 2 ax's, we will have 4 of them. And now when we go to look at this, we need to differentiate it. So doing that, what are we going to get? The 2x squared will become 4x, which is nice. That's matching up with what we've got down here. Our 4ax is going to be 4 lots of a, and our 2a squared is going to disappear. It's a constant, so it has no rate of change, not changing at all. So now the next bit to look at, this thing should equal 4x plus 10. So if we actually just look at the kind of powers of 10, the powers of x where x is 0, and on the left-hand side we get 4a, on the right-hand side we get that 10. So a is 10 over 4, which is 5 over 2. Lovely jubbly, nice and quick one there. Let's go to number 7. What have we got then? So the straight line L1 passes through the point A, which is minus 7 minus 4, and meets the y-axis at point B, which is 0, 2. Okay, that's nice. Determine with full justification whether the point minus 5 minus 2 lies above L or below L1. So firstly, let's find the equation of L1. We have a coordinate and we have the y-intercept. So we already know plus c. The c is going to be 2, which is nice. We just need to find the gradient then. So the gradient is always the difference in the y's over the difference in the x's. So difference in the y's, let's do a take b, minus 7 take 0, over, again, a take b, minus 4. I've done that all upside down. Let's start again. So y's, minus 4 take 2, over the x's, minus 7 take 0, minus 4 take minus 2, or take 2 is going to give us minus 6. Minus 7 on the bottom take 0, which is minus 7. So we just get 6/7 altogether. So that's the gradient. And like I said, this goes through 0, 2. That is the y-intercept. So the line L1 is going to be y is equal to 6/7 plus 2. We then want to find whether minus 5 minus 2 is above or below it. So let's plug in that x-coordinate of minus 5. When we look at y of minus 5, we'll have minus 5 times 6/7, so that's minus 30 over 7, still plus the 2. Let's put that into one fraction. 2 is the same as 14 over 7, and 14 take 30 is minus 16 over 7. This number, if we kind of write it as a mixed number, is minus 2 and 2/7. So this is smaller than minus 2. So that tells us that it's going to be, the point is above even, the line is below. We can kind of draw it out where we've got the 6/7 going across, something like that. We get this coordinate here of minus 5 and then minus 2 and 2/7. And then the point is going to be above that at minus 5 minus 2. So the point is, in this case, above. Not below, but above. So the line is below, the point is above. Part B, the straight line L2 passes through the point minus 1, minus 10, and meets the line L1 at B. So we have the same y-intercept. Determine with full justification whether the point Q lies inside or outside the triangle ABC. Okie dokie. So, again, we need to find the line L2, really. We again have a point, and we have a y-intercept. We can be a little bit sneaky and just think, okay, it's at 0, 2 here, and at minus 1, 10 here. What the gradient represents is for every step to the right, how many steps up do we take? So going from here to here, we've gone from minus 1 to 0. So we've taken one step right. So the difference in the y's is exactly the gradient. So we've gone from minus 10 to 2. The gradient must be 12. So for line L2, we know that y is equal to 12x plus 2. And again, we could plug in minus 1 in here just to double check that we do get minus 10 as our y value. So now we've got our two lines. We need to figure out whether the point Q lies inside or outside that triangle. Might be worth us drawing this out. So thinking what we've got here, let's just have a little axis going on somewhere down here, where most things are happening negative, which is a little bit strange. But what points have we got? B is going to be at 0, 2. C is at minus 1, minus 10, so all the way down here. So that's C, that's B. And then point A, where was point A? Point A is minus 7, minus 4. So it's going to be above B, below B, but above this C. So actually, if we kind of scale this a little bit, let's move this up a little bit. And it's going to be somewhere over here. This is not a perfect sketch. Doesn't need to be. But then the question is whether Q then, think about where it could be, minus a half. Well, the C has the coordinates of minus 1. So Q is somewhere along this line. So we need to find out whether it's above or below this line and above or below this line. Which lines are they? Let's actually think about what we did to figure out, like this triangle. B and C we used to find line 2. So this bottom one is line 2. And then we used A and B to find line 1. So this bottom line is line 1. So the top line is going to be line 1. So now then we just need to take the point Q and figure out whether it's above or below both of these lines. So let's go and plug it into line 1 to begin with. So if we look at line 1, if we plug in minus a half, we'll have 6 over 7 times by minus a half plus the 2. Doing that, a half of 6 is 3. So we'll have negative 3 over 7 plus a 2. 2 again is 14 sevenths. So this is 11 sevenths, which we can see is much bigger than minus 5. So line L1 is above Q. So that's kind of limited. If you think about this green line again, Q's not up here. It must be somewhere down here. So we need to go and check on line 2. Are we above or below that one? Exactly the same process, but it's replacing the line 1 with the line 2. Line 2 is over here. So when we plug in minus a half, we'll have 12 lots of minus a half plus a 2. Half of 12 is 6. Negative 6 plus 2 is going to give us negative 4. So what we have is that this point is minus 4 on here. And if we look at the actual Q value, it was minus 5. So what we've got is that Q should exist somewhere here. So that's going to be point Q. Like we said, this was minus 4. And where we worked out this one earlier, that was 11 sevenths. So we can see there that Q is below the triangle completely. So Q is outside the triangle ABC. So yeah, just in case, if something's out of shape, just check all the lines of the shape, see if you're above it, below it, and then do a little drawing to see whether that actually puts you inside the shape or outside the shape. Lovely jubbly. Question number 8 then, as we move on, is something exponential. We've got a table. Give me one sec, just dropped everything. Yeah, we've got some table here. We need to figure out basically the exponential stuff that's going to go on down here. So we've got lots of numbers going on. A and B are non-zero constants. Use a graphical method involving logarithms to show that the above data is consistent with this assumption. Use a graphical method. So I'm going to guess then that we're going to plot log of P. Because if we think about this, let's take logs of both sides. We can have log p, and I'll do natural log. Why not do natural log? Natural log of p is going to be the natural log of a t to the b. How do we split this natural log on the right-hand side out? Well, the first thing is to use the addition law. It's going to be the log of a plus the log of t to the b. And that log of t to the b, we're able to bring the power, that b up there, to the front. This is again still equal to log p. I will put some brackets around everywhere, make it a bit nicer looking. So this now looks a bit strange, but it is in the form of a straight line. You've got your y, you've got your x coordinate is t. So effectively this is going to be the x over there. B is then the gradient, it's m. And the log a, is going to be our c component. So this is a straight line, just in a kind of strange format. So what we need to effectively do is go on, find the natural log of p for all of these, which I will do quickly. So natural log of 20, we'll do 2.99, it's exactly 2.905, so it is 3.0, I suppose. If we do 64, we get 4.16. Let's do 110, 4.70, 180 gives us 5.19. For 260, we get 5.56. 320 is going to be 5.77. And for the 420, it's going to be 6.04. So ideally then, when we actually go and plot now, the natural log of p against t, we should see that this follows a straight line. And that shows that this assumption that we've made about the relationship between p and t was true, because we're able to plot log of p against t as a straight line. So now it's just a case of going through. Obviously, I haven't got graph paper or anything here, but you'd go through and just plot all of these on a nice graph. I imagine in the exam they'd give you graph paper to do this with. You plot it all on, sure it's a straight line, and that shows that everything is going to be completely fine. So yeah, if we've got 3, t is going to go from 2, 4, 6, 8, 10, 12, and 14. 2, 4, 6, 8, 10, 12, and 14. And now we're going from 3 up to 6 in a bit. So let's start counting there at 3, 4, 5, and 6. It's not going to be a perfectly accurate graph, but as long as we're showing everything that we need to show, that should be fine. So we've got 1 point at 2, 3. The point with 4 goes to 4.16. Then we've got 4.7. This doesn't look like it's going to work, does it? Then 5.19. I feel like one of them's wrong. Have I got one wrong? And what's the gap here? The gap here is 0.5. Then it gets smaller. It's getting smaller and smaller. Silly me. I need to do log t as well. So yeah, very silly of me there. So yeah, this graph, I need to go through and get log t of everything as well. So log t, log of 2, 0.69. Of 4 is 1.38. Of 6, 1.79. Of 8, 2.08. 10, it's going to be 2.3. 12, we have 2.48. And then for 14, we have 2.64. So yeah, now we want to just change ever so slightly what I was doing over here, where this now should run from 0, all the way up to 3. So let's spread this out a little bit further. That can be 1, that can be 2, and that can be 3. I will spread out a little bit more just because we've got not quite up at the high end. Something along those lines. My sketch is not going to be perfect. If you had proper graph paper, this would be a little bit easier and more accurate to be doing. So yeah, we need to be plotting log t and log p. Like x is log t, y is going to be log p. So doing that, what do we get? We get 0.69 and 3. So something around about there. Then we get 1.38 and 4.16. So roughly doubled, 1.38 and 4.16. Then we get 1.79 and 4.7. So we should see that these end up forming a straight line. This goes like this. My graph is not going to be perfect, but we should see that these all end up, plotting themselves in a straight line here. And like we say, what's that shown? Due to our kind of log rearrangements earlier, where we started with their assumption, rearranged into a form of y equals mx plus c, where the x was log t, the y was log p. So from there, that is a straight line graph. We can show that if that's a straight line graph, that this assumption was correct. And the data that we've got, as we plug everything in, does give us a straight line, which is all good. For the value of a and the value of b, we need to find the y-intercept for a. I was thinking this is going to be the y-intercept, and then the gradient for b. So for the gradient, what we can do is, we'll actually use the data that we've got over here. So I'm going to have the coordinates of 2.64 and 6.04 and 0.69 and 3.00. So what is the gradient here? Difference in the y values is 3.04. Difference in the x values is 1.95. So doing the division there, what does that give us? 3.04 divided by 1.95. We have an answer of 1.56-ish. So that's for the gradient. So that is exactly b. Because we can see the gradient was just b in this case. So for the y-intercept then, what I'm going to do is actually just form the straight line equation using one of these points and our gradient. So we know that y minus y1, so let's say 3, is equal to the gradient of 1.56. Lots of x, take away 0.69. And now what do we want? We want the y-intercept. We know the x coordinate there is 0. So this, we don't need to kind of fully rearrange it. We just want to find y when x is 0. So if we do that, what do we get? Y is equal to 3 plus 1.56 times by negative 0.69. So we can go whack that in the calculator, see what number it's going to give us. 3 plus 1.56 times by negative 0.69. So we get this value of 1.9236. And that is our y-intercept. In our kind of rearrangement, that is the natural log of a. So this 1.926 is equal to the natural log of a. So a itself is going to be e to the power of 9236. So doing that, what do we get? E, where's e? E's there. E to the power of the thing we just found gives us a number of 6.846. ... Yeah, lovely. So a bit strange here. Not quite a normal question that you're going to see, but one where we have this idea is quite common actually. So having the rearrangement of this looking structure into something that is a straight line graph happens a lot in physics. So if you do maths as well as physics, you'll be quite common with this idea, especially when you're doing kind of experimental stuff, that then you can use to show that it is like an exponential relationship between the two variables. Lovely jubbly. Let's have a look at question number 8. So first of all, not even looking at that's an integral in it somewhere. Something to do with integration, and they're most likely. So what have we got to do? We get given a cubic. Figure 1 shows the graph of the curve for this equation. X cubed minus 9x squared plus 24x plus the 9. The straight line L is normal to C at the point A. Okay, so this in here is a little right angle. It's not a very good square. Yeah, a little right angle. Whose x coordinate is 5. Okay. So the equation of L is this. Okie dokie. So we want to find the normal of this curve at the point 5, like when x is 5. To do that then, we need to first differentiate. So taking that y, and we'll get the dy dx. X cubed is going to be 3x squared. I'm going to need more space than that, so let's go over here. Minus 9x squared. 9 times 2 is 18. drop the power down to 1, and the 24x, nice and simple, 24. We then want to plug in the number 5. The first thing I'm going to do though, I'm going to factorise out a 3. This looks like it's got a nice bit that could be factorised basically. So 3x squared minus 6x. Why am I doubting myself? Yeah, plus 8. Couldn't do 3 times 6 then. Does this factorise nicely? I don't know if it does. Yeah, I'm not entirely sure if it does factorise nicely. So I will just leave it like that. We don't need to do that. So let's find our gradient of the tangent is going to be dy dx when we sub in the value of 5. So doing that, we're going to have 3 times by 25 for 5 squared. Take away 6 times 5 is 30, and then plus 8. That gives us 25 minus 30 minus 5, plus an 8 is a 3. So that gives us 9. That's always a good sign. When you look down at the answer, it has a 9 in there, so that's always good. So that's the gradient of the tangent. So that tells us the gradient of the normal is the negative reciprocal of that. So minus 1/9. We now have that. We also then need the coordinate that's happening at A. We know the x coordinate is 5. Let's just find the y coordinate by subbing 5 into the original cubic we have there. So doing that, y is equal to 5 cubed, 125, minus 9 times 5 squared. So 5 squared is 25, times by 9 will give us 225. I'm going to take that away, and then add on 24 times by 5. 24 times 5 is 120, and then we're going to add on a 9. So doing this, what do we get? These together are minus 100. Add 120, gets us a positive 20, and then we should have another 9 to get us to 29. No 29's in there, but I'm hoping that 29 and a 9, does that make 226? We'll find out in a second. If not, I will just double check some of the maths I've got. So now what do we have? We need to do y minus y1. So y minus 29 is equal to m, which was minus 1/9 of x minus 5. So let's expand the brackets. It's actually probably easier to times by 9. So over here as well, we want to have 9y at the end. So instead of making like a 9th of x, just make 9y even. So 9y, what is 29 times 9? Not what I want to do in my head. It's 261. And this negative then, we'll expand this bracket with the negative. So the 9 we've kicked to that side. The negative will leave over here to give us that this is 5 minus x. And let's just add over to the other side. So we'll have 9y plus an x. And then looking at this, we want to add over the 261 with the 5 to make the 266 that they're looking for. So that's all good. And it's always nice when they actually get the correct answer and it's giving you exactly what they showed you in the show that, and you end up with that solution. That's always good. Part B then, we want to find the area of the finite region bounded by C, L, and Y, and show it's approximately 20 square units. So that's obviously this shaded thing in here. So to do that, I will first shrink down all the work I've already done. We will need some parts of it, so I'm not going to get rid of it, but we'll just leave it up there for a second. So what do we need to do? We need to integrate, and integrate between 0 and 5, but not just of the function itself. That would give us this area underneath. We want to do the difference of these functions. So we're going to integrate from, again, 0 to 5. What was the equation of our normal? We've got it here, but we want it in terms of y equals. So let's get that very quickly. So we'll take away an x. So we'll have 9y is equal to 266 minus x, and then divide by a 9. So y is 266 over 9. I don't think that's going to divide nicely. I think that 261 was 9 times 29. So we've added on 5. We've not added on enough 9s, basically. And then, again, x over 9. Nothing nice we can have about that one. So we've got that function, 266 over 9, take away x over 9. And we need to take away then the curvy one. We've got the little cubic down here. So take away this entire thing. So take away x cubed. We have a negative x squared in there. So we're going to add on those 9x squareds. Take away 24x and take away a 9. We could go through and like collate these bits. It's probably the right thing to be doing, but we're not going to get very nice numbers from doing that. I will still do that, but yeah, it's not going to give us the nicest numbers in the world. So what do we get? Let's start with the highest power still. X cubed. We still have the same limits as well. The 9x squared, that's not affected. So now we have negative 9x, so negative a ninth of x, and another negative 24. That gives us, in the calculator, negative 217 over 9 lots of x. And then let's take that 266 that we've got at the start, this bit over here, and our minus 9, combine them together. So 266 over 9, take away 9, gives us 185 over 9. 185 over 9. Now then, yeah, we've collated all this, got it back into kind of cubic form. This refers to then the difference between these two. So this should have roots at 5, like it should have a root at 5, that equation. Now then, let's actually perform the integral. X cubed, what does that become? It's going to be x divided by 4. The 9x squared, raise the power to cubed. 9 divided by 3 is a 3. As well, this is a negative. I still need to have the negative out the front. Let's raise the power there to x squared and divide the 217 over 9 by 2. 217 is an odd number, not divisible by 2. So let's just double the 9 to an 18. 217 over 18. Again, negative from the bit above. And the 185 over 9, that's all going to end up with just an x next to it. We then need to plug in our limits of 5 and 0. Everything we have in here is like a polynomial term. It's just a constant and a power of x. So the 0 itself is going to do nothing. This will be 0, this will be 0, this will be 0, and this will be 0 as well. So just lots of zeros for the 0 part. The 5s, though, yeah, not going to be the nicest thing in the world. Just in case now, whack this all in the calculator, see what's going on. So we will do that. What I suggest to do is normally I'd write in answer for x, and then like save 5 and then go back up and look at the answer stuff. But where we're just plugging in one value, it doesn't matter too much. So we need to have negative a fraction of 5 all to the power of 4 over 4 plus 3 lots of 5 cubed minus 217 over 18 lots of 5 squared plus 185 over 9 times by 5. And we get a number here that is, yeah, so we were looking for something that's approximately 20 square units. The answer that we get when we actually sub everything in there on the calculator was 725 over 36. That is, if we were to write it out in kind of decimal form, just give myself a bit more room there, 20.13, and then the 8 is recurring, just the 8 being repeated at the end there. That's approximately 20, isn't it? That's close enough for me. It's within 1%. That's, yeah, I'd say that's approximately 20. That looks like everything is going to be all spot on. Lovely jubbly. How many questions have we got left to go? That was 9. Here's 10, 11, 12, 13. Yeah, I've got half an hour. So that should be enough time to do it all. So, number 10. We have some cubic. Show it has only one stationary point and determine its nature. Okie dokie. So to do that, how do we find the stationary point? We need to differentiate. So we're going to take this cubic and we're going to differentiate it. So dy dx on the left. What does x cubed become? Bring the power down the front. So 3 times 1 is 3. Drop that power down to 2. We'll take away then. We're going to have 3 times 2 is 6. Drop that power to 1. The 3x will just become a 3. And the 5 vanishes. 5 is a constant. How fast do constants change? They don't change. So the dy dx is just 0. This then, we want to show that it only has one stationary point. So we need just a quadratic to have one root. So we need to show that it is, basically this should be a square quadratic. It's going to have a quadratic with a repeated root on the bottom, like this, where that's exactly what's going on. So let's try and factorise this. First thing I'll do is I'll take a 3 out. X squared minus 2x and plus a 1. And this bracket then, we need a number, we need two numbers that time together to make 1 and add together to make minus 2. What numbers do that? Both of them being -1. So this should be x minus 1 all squared like that. And again, still with the 3 at the front. So when does this equal 0? Whenever x is 1. So that's the position of it. We know to define its nature. To find its nature, that means like, is it a minimum, is it a maximum, or is it a point of inflection? So to do that, we need to find the second derivative. We can do that in two ways. We can either do it with this equation, or we can do it with this one. Both will give you the same expression, but maybe in a different form than the other one. So the 3x squared, 3 times 2 is 6. Drop the power down from 2 to 1, and then minus the 6. We can factorize this out to 6x minus 1, which you could have seen from the chain rule there. 2 times 3 is the 6. Drop the power down to a 1, times by the differential of x minus 1, which is just the 1. So to do this, setting that not equal to 0, but plugging in our value of 1. So if we do, 3y dx squared, evaluated when x is 1, we get 6 lots of 1 minus 1, which is 0. So we get a big fat 0. This then is kind of inconclusive. It doesn't tell us it's a min, doesn't tell us it's a max, doesn't actually tell us much at all. But the fact that we only have one stationary point on a cubic means that it must be a point of inflection. Because you think of what options do we have, it's either going to do this sort of idea or the upside down of that, where you clearly get the two different turning points, or these get pushed together and you end up in a scenario where it just kind of goes flat and keeps going. So we know it's going to be a point of inflection. We just need to now show it's a point of inflection. So to do that, I'm going to look just either side of our point. So looking at say like 0.9 and 1.1, and then seeing what do we get here. But another way we could do it as well is thinking about dy dx. So dy dx was equal to 3 lots of x minus 1 all squared. So we know dy dx is equal to 3 lots of x minus 1 all squared. Anything squared is positive. 3 times anything positive is positive. So this is always positive. So we've got the idea that it's always positive or 0. I suppose it could be 0 as well at that point. But either side of that then, it's never going to be negative. So this exact scenario is going on where it's increasing and then like just goes flat for the split second at the turning point or the stationary point and then keeps going again. So because we've got that idea and this idea over here, we have that it's going to be a point of inflection. It's a proper name for it. A point of inflection. So that tells us that. Those two combined tell us those bits. Again, you could plug in like 0.9, 1.1 and just see either side, like what does dy dx become? But we know straight away it's just going to be positive. So we don't actually need to do that process. If you didn't have such a nice, like simple expression to work with, as dy dx, you do just plug in values very close to your turning point or your stationary point and then see like, is the gradient increasing or decreasing either side? Let's keep going. So a circle has this equation, x squared plus y squared plus 4x minus 10y plus 9 equals to 0. Find the centre and find its radius. So to do that, let's just to kind of treat the x's differently and the y's differently. We're going to complete the square on the x's. So we'll have x plus 2 all squared, take away 2 squared, where that 2 and this 2, it's the same 2, comes from half of that 4. Similar process with the y's then. We'll have y minus 5 for half of that 10. Again, the minus, like this was positive because this was positive because this was positive. This is negative because this is negative. And then we need to take away a 5 squared. These bits are always negative. Imagine if we expanded this bracket, you'd have a plus 5 squared at the end. So this just cancels off with those ones. And then we still have our plus 9 from the original equation. And let's just slightly rearrange then. We'll get all the brackets here, x plus 2 squared and the y minus 5. And take all of the other numbers to the other side. So here we have minus 4, and this is minus 5 squared, so 25. So together they make minus 29. Adding a 9 to that is minus 20. putting it on the other side is going to be positive 20. So this is equal to 20. So therefore, what we have is our centre is equal to minus 2, positive 5. And our radius is the square root of 20. So this is basically Pythagoras. If we think about just drawing a circle quickly, what they're really saying about a circle, every point is this far away from the centre. It's all the radius away from the centre. So if we were to pick any other random point on there, how can we actually find that? We know that this distance should be r, but then we have the kind of like difference in x's and difference in y's to form a right angle triangle, where this is going to be, the one bracket, x plus 2 is going to be this far, the y minus 5 is going to be this far. So we should have, Pythagoras, 1 squared plus the other 1 squared equals the radius squared. So therefore the radius is the square root of this, and it's going to be the square root of 20. Let's keep going then. A tangent to the circle passes through the point with coordinates 0 and minus 1 and has gradient m, where m is less than 0, so negative. Show m is a solution of this equation. So let's actually repurpose our drawing here, and let's fill in a few blanks that we've got. Let's get rid of all this stuff, and let's draw on exactly what's going on here. Stretch that a little bit. Ooh. Come on. So where was our centre? It was at -2 and 5. So where is the x-axis going to go, and where's the y-axis going to go? If we just draw them over here for a second, then we can move them onto our circle. So we needed to make sure that our centre's to the left of our axis, and it's also above our axis. So it should be something like this. And we can see that we're going to go through the point 0, minus 1. So that point that we have is down here somewhere. X coordinate 0 and y of minus 1. Tangent to this passes through where m is negative. So something doesn't look quite right there. Because this should be tangent to the circle, passes through the points. Okay, so that point doesn't have to be on the circle, ignore me. But we need to make sure that we are negative. So let's actually, if we plug in x is 0, what y coordinates do we get? So we'd have like y is going to be root 20, plus or minus root 20 plus a 5. Root 20 is bigger than 4 but less than 5. So actually our x-axis is down like that. So both of our points cross over like in the positive y values. So now we've done that, what else can we do? I'm going to make this a little bit neater if I can, try and make it, over there, something like that. Move that to the centre. So, we're going to go through that point of 0 and minus 1. So we're down here, and we need to have a positive gradient. So how can that happen? Two possible ways. Let's actually stretch this a little bit more. One of them is we could have a line that goes from here to here, something along those lines. I'll just move that down into the correct place. Or it could be from up here. So they're the kind of two possible cases. I will try and get that to match up correctly. That's not the right way. Let's just draw it from there. So we have this sort of idea. One of these two blue lines is like the tangent we need. Both of them with positive gradient. Both starting off down low in the kind of this quadrant. They will end up in this quadrant. This one, if you extended it, it would get there eventually. So how can we do this? We need to find a tangent to the circle. Few ways we can do that. I think the easiest is just to differentiate. So when we go and look at this, do like implicit differentiation. So the x squared is going to become 2x. The y squared is going to become 2y dy dx. So basically, when you've used the wrong letter, just whacking a dy dx in there. So like we used y when we should have used x, hence the dy dx. The 4x becomes a 4. The minus 10y, same idea. It's going to be minus 10 dy dx. And that will all equal to 0. So dy dx all together, if we factorise for it, let's bring everything that's not dy dx, so the 2x and the 4 to the other side. So minus 2x, minus 4. And then what bits do we have on the dy dx? A 2y and a minus 10. So that's the gradient of every single point that we have here. We need to make sure then that we have a line that has this gradient, where x and y are points on the circle. And it's going to go through this point of 0, minus 1. So this is basically our m. This is going to be some coordinate that we have. And we know c then is minus 1. So y is equal to this thing, minus 1. So the gradient is m, that's this thing. Okay, I think I've overcomplicated it and actually found out what m is going to be. So then pick one of c. Yeah, so we're kind of skipping ahead a little bit, but we can kind of backtrack and just go through and find this sort of idea first. So let's think of a way we could do this. How can we do this? This point we know is minus 1. We have these points here. We know some facts. So we know if we were to kind of like draw from the centre to there, that should be a right angle. This as well should be a right angle. They're both tangents. Okay, maybe this is more geometry. These lines are the same length. These lines are the same length. There should be a line going through here then. Is that going to work? Seems a bit not so succinct. How else could we do this? Tangent to the circle C passes through the points with coordinates 0, minus 1 and has gradient m. So we know that the tangent is y equals mx minus 1. We need to make sure then that we hit our... Okay, yeah, we need to make sure we hit our curve exactly once for each value of m that we could have. So let's take this tangent equation and sub it into our expression for the circle. So x plus 2 all squared. I'll actually do it on this one. So yeah, it's x squared plus y squared, so plus this thing squared. So that's going to be m squared x squared plus 2mx plus 1, so minus 2mx. For the y parts, sorry, the 4x is just 4x. Take away 10y, it's going to take away 10mx, and then plus a 10. And we'll shift everything over a little bit, just so I'm running out of space. So minus 10x plus a 10, and then we have plus a 9 as well, equals 0. Let's try and collect some of these bits. How many x squareds have we got? Over here, I've got m squared plus 1, lots of them. And that's it for x squareds. So we can kind of like cross those bits off. For the x's, I've got d, and d. So what do I have here? Positive 4, and then I've got negative 2m, negative 10m. So that's negative 12m. So 4 taken away 12m times by x. That's going to be a plus. And then the numbers, I've got a 1, I've got a 10, and I've got a 9. So that gives me a 20 altogether. So plus 20 equals 0. And like we say, yeah, so this, they do touch it, but they're like repeated roots. So where we have this quadratic, the discriminant must be 0. So when we look at the discriminant of this quadratic, b squared, so 4 minus 12, 12m, all squared, minus 4 times a of m squared plus 1, times by c of 20. Like I say, that should equal 0. Let's expand some of these brackets. This is not so nice to expand the 4 and the 12, but we could factorise a 4 out the front first. So that's going to give us like a 16 for 4 squared because of the square. And then what we're left with, just very quickly then, is 1 minus 4m. So if we're trying to expand that out, we're going to have 1 squared is 1, minus 8m, and then plus 16m squared. We're going to take away, so this 4 and this, so 4 and the 20 makes 80. So 80m squared and 80. Take away 80 equals 0. So nice now, the 16, these numbers are multiples of 16. So we can divide off by it. I'm just going to shift everything. No, we'll try and go. Yeah, we will use this stuff. So yeah, dividing everything by 16. We have the 1 minus 8m plus 16m squared minus 5m squared minus 5 equals 0. And then from here, hopefully we can just rearrange to this bit. I am going to now take this up to this corner. Actually, no, let's just shrink everything over here down a little bit and carry on where we were. So all this stuff, let's shrink it down. I've only got 10 minutes. How many questions have I got left? 2 more. I don't think I'm going to get everything finished today, unfortunately. So yeah, we're working from here now. What do we have as well? How many m squareds? 16 minus 5 is 11. That's not a good sign. Minus 8m. And then minus 4 is equal to 0. So yeah, something seems to have gone wrong there. Because we should be able to kind of divide this off into these bits. Did I make any mistakes earlier on? Don't think so. Yes, I did. This should be a 3. So 4 times 3 is 12, not 4 times 4. So changing that to a 3, how does that change everything else? Looking down, this would then become 6. And this would become 9. So 6 in there, 9 in there. So yeah, that would be a 6. This would be a 9. 6 and 9. And then as we actually rearrange that, let me just put this back on the correct line. It's not going to fit, but I can move this first. So starting from there again. Now how many m squares do we have? We have 4m squareds for 9 take the 5. And we've got a minus 6m and a minus 6. Sorry, minus 4. 1 take away 5. So again, yeah, we can divide by the 2. So 2m squared minus 3m minus 2 is equal to 0. So yeah, nothing wrong with making little mistakes as we go. It's always good to think like, okay, we've got something that's very, very close, like what could have gone wrong and where could it have gone wrong. That's all looking good. We now need to find the coordinates of P. So actually go and find like these blue points that I've put on here. So doing that, what do we need to do? So solving m then, what gradient can m be? So thinking about that, m here, if we were to actually solve this equation, let's use the quadratic formula. Actually no, so you'll have a calculator. In these exams you have a calculator you can just solve these with. So I'm going to use Wolfram alpha, plug in the quadratic of 2m squared minus 3m minus 2 equals 0. What numbers do we get for m? We get out not very nice. Oh no, actually not too bad ones. We get 2 and minus a half. So we knew that m had to be positive. So in that case, m has to be the 2 that we have there. And from this then, we know the equation of the curve is going to be y is equal to 2x minus 1. As in just filling in the m from here. And we have our, our equation of the circle. So we can now take this exact thing and plug it in there. So doing that, what are we going to get? Again, x squared, x plus 2 all squared will be x squared plus 4x plus a 4. Y minus 5, so this thing minus 5 is 2x minus 6. So doing that, expanding that bracket, you'd have 2x squared is 4x squared. The 2x minus 6, so times them together is minus 12, double it minus 24. And then let's think about the 6 would make a 36. And all of those bits, we add a 9. Oh no, we don't add a 9. No, that's equal to 20. Let's collect some terms. We've got 5x squared. How many x's have we got? Negative 20. How many numbers have we got? I've got a 4 and a 36. And then take away a 20. Gives me a positive 20 on this side. Let's divide everything by 5. X squared minus 4x plus 4 equals 0. So this is going to be x minus 2 all squared equals 0. So x must equal to 2. And it's good that this is a square quadratic because we knew it was a repeated root here. So that's a good sign of it's working correctly. For the y coordinate then, we simply double it, take away 1. Double it is 4, take away 1, gives us 3. So our final answer should be 2, 3 as the coordinates. Lovely jubbly, bit of a long-winded one there, but it was worth a lot of marks. I think that's 14 marks altogether. So a decent chunk of the paper there. Like I say, I've got a lesson at 6 at 7, so fingers crossed we can get these two done in time. Let me just reply to this message. So yeah, question number 12. We have to solve this in terms of degrees. So we have tan to the 4 and tan squared. So this is a quadratic, hidden quadratic, where we have like tan squared as the base of it. So let's just think about having x squared is equal to 6 plus x. Let's try and solve this. So x squared minus x minus 6 is 0. We'll have x minus 3, x plus 2 equals 0. So what that's going to tell us then is tan squared of y is equal to either minus 2 or 3. So tan squared can never be minus 2. It can only be positive 3. So tan squared is going to equal 3, or tan by itself is going to be the square root of 3. So if we do the inverse of tan at root 3, what do we end up getting? Let's ask the calculator. Inverse tan of the square root of 3. We get 60. And then that's going to be the principal value. So between minus 90 and 90. We can then think about kind of adding that over. So adding 180 to get to the next range that tan works in. So we should have answers of 0 and 60, 60 and 60 plus 180, i.e. 240. So that was, yeah, nice quick 7 marks compared to some of the ones we've seen before. Last question then. Again, another hidden quadratic. This one we had powers that would double each other, so 4 and 2. Here we've got one power positive, one negative. So that's another scenario of a hidden quadratic. So here, same sort of idea. I'm going to set that equal to 0. So e to the x plus 10 e to the x, or e to the minus x, minus 7 is 0. Let's times by e to the x. So this is e to the x squared, plus a 10, which I actually put on this side, and then minus the 7 e to the x equals 0. So this is, yeah, a quadratic in terms of e to the x. Factorising this, we need to make 10, so you can have 5 and 2, which does make a 7. So we'll have e to the x minus 5, e to the x minus 2, all equals 0. So therefore e to the x is equal to 2 and 5. So x is equal to the natural log of 2, or the natural log of 5. So that one not too bad. These quadratics are normally quite simple as long as you can spot where they are. For the next bit then, solve this thing. So how is this different? What's changed? This is very similar to what we had over here. So actually if we let y equal x minus 1, what happens? We're going to have e to the 2y minus 7e to the y plus 10 equals 0. This is the same thing. I know I've got it there as e to the x all squared. If you expand that, it's e to the 2x. So exactly the same expression. So what we're saying is that y has those solutions of log 2 and log 5. So x is going to have the solutions that are 1 bigger than that. So x is going to be 1 plus log 2 and 1 plus log 5. Lovely jubbly. So that is, yeah, the last question. I did want to go and just double check some stuff from the pages beforehand. And just make sure that I've got no mistakes in them. So that's question number 2 and question number 4. I do only have 5 minutes to my lesson, so I may well have to be in a rush, but we will find out. So question number 2, yeah, it's this negative thing with the inequality. So let's actually just look at the, yeah, with the time, I'm going to look at the answers just to give you the answers for it, so you've got nothing missing. I think I might have just overcomplicated it a little bit. What have they done? Okay, yeah, I've just forgot this idea. So instead of trying to think of it as 2 cases, what we're going to do is times both sides, top and bottom, times the left side, top and bottom. So the 4x plus 1, x minus 1, times it by x minus 1 over x minus 1. So on the bottom, you now have x minus 1 squared, and on the top we have 4x squared. You'd have a negative 4x plus an x, so negative 3x, and a minus 1, still bigger than 3. Let's actually go to the other side quick. And then from there, times over by the x minus 1 squared, so 4x squared minus 3x minus 1 is bigger than 3x squared minus 6x plus 3. Let's make this into a quadratic. So we're going to have single x squared, we're going to have a positive 3x, and a negative 4 is bigger than 0. Factorising this, x is, x minus 4, positive 4, x minus 1 is bigger than 0. So x would be equal to 1 and minus 4 if this was an equation, but it is an inequality, so we want this to be positive. So when is it a quadratic positive? Outside the 2 roots, when it's a positive quadratic. So here we end up with either x is less than minus 4 or x is bigger than 1. Lovely jubbly. So the last bit to look at was just number 4. Just a double check. Don't overcomplicate it. I think I just overcomplicated the first part of it again. We get a number of, -7. I was right the first time. So thinking what's happened, we need to take our equation. X now, let's replace it with a half of x plus 1. So 2 lots of a half x plus 1 plus 5 all squared equals 0. So that tells us, well, 2 lots of a half is 1. So x plus a 2 plus a 5 is plus 7. All squared is 0. So x is going to be -7 as our final answer. Lovely. Like I say, I am strapped for time. That's perfect timing really to get it all done. Any questions, please leave me a comment or something. But if not, hopefully that's all helpful to anyone that needs these papers or anything. So thank you very much for watching. I don't know when I'll do another one. Maybe tomorrow, maybe Saturday, maybe Sunday. Depends how busy I am, how I'm feeling. But have a nice couple of days. Have a nice weekend and stuff. And I will see you hopefully on the next video. I love you. Cheers. Bye. Is that stopping? No, now it's stopping. No, cheers.